This presentation highlights the design, build, and test of the EZ-ON Load Center. Group A, Isaac Tritt, myself, the team lead, Peter Petrovich, Randolph Parker, and Samuel Snow. This is the EE4800 Senior Design Project at Kennesaw State University, and our professor was Dr. Cyril Okayo. Acknowledgements. Group A would like to express our sincere gratitude to our advisor, Cyril Okayo, for his continuous support, guidance, patience, and immense knowledge in all the time of research and writing of this thesis. We would also like to thank our professional electrical engineering consultant, Bill Womack, for his insightful opinions, suggestions, encouragement, and insightful comments throughout our research and design process. We would like to also thank our families and friends for their support throughout the writing of this thesis. We could not have done this without their constant support and encouragement in order to fulfill our educational goals and soon graduate as Bachelors of Science in Electrical Engineering. Before beginning the design, build, and test process, there must be a problem. This slide showcases the problem statement. So currently, electrical contractors and electricians are contributing a lot of time towards the installation of electrical load centers, mostly in residential homes or commercial properties. This installment period is mainly contributed to the wiring of each circuit breaker, which is located inside of the load center. Each circuit in the home or commercial property must have a circuit breaker. The electrical equipment manufacturers have attempted to address this issue, but have evidently fallen short. The most innovative load center out on the market today is a plug-on neutral load center. This load center has only reduced half of the issues that are responsible for the extensive installment times. The objective of this research is to develop an electrical apparatus that will reduce the amount of time it takes an electrical contractor or electrician to install a complete set of circuit breakers in a residential load center. A plug-on neutral load center was designed to eliminate the wiring of a pigtail, the breaker's connection to the neutral bus, by creating a neutral bus that the breaker snaps into. This design is estimated to reduce the installation time by about 30 minutes compared to a traditional load center. In a traditional load center, there must be two wires landed on the back of the breaker, the hot wire and the neutral wire, and if it is a GFCI type breaker, there must be an additional pigtail wire landed on the neutral bus. The EZ-ON Load Center is the latest breakthrough in residential electrical distribution. The EZ-ON Load Center aims to eliminate all wires going to the breaker and create a completely plug-on system. It provides electrical contractors, electricians, and builders the ability to quickly assemble residential load centers in a simplified process. Ultimately, the expedited electrical installation of residential load centers will save capital and construction costs for contractors and builders. This load center also reduces the installation complications that are experienced by electricians when installing the circuit breakers in residential load centers. Ultimately, this EZ-ON Load Center was designed to simplify the landing of the wires. If you can land all the wires before installing the breakers, you are more likely to land the wires cleanly, neatly, and organized in the best manner possible without the breakers getting in the way. Shown here is a normal Siemens plug-on neutral breaker. You must land the wires in the back of the breaker before installation. As you can see, it can be a little cumbersome making sure the wires are landing appropriately and tightened down to their specifications. Once the wires are tightened down, then the installation is finished. If you're going to remove this breaker, you must also remove these wires again. With this EZ-ON system, the installation process is streamlined. There is no need for a wire connection to the breaker. The wire is already landed, and the changing of a breaker is much simpler. As you can see, the wire is coming into the load center as it normally would. The ground wire is connected to the ground bus. The hot and the neutral wire comes to our EZ-ON connection system.
For the project design, The manufacturers of the load center and circuit breakers were Siemens, Square D, and ABB. It's important to note that the Siemens plug-on neutral load center was re-engineered to create the easy-on load center. The first goal of this project was to ensure that the estimated time it took to install the easy-on load center circuit breakers was quicker than that of its predecessors, the traditional and plug-on neutral load center. The second goal of this project was to reduce the amount of money that electrical contractors and builders were spending on labor that was associated with the amount of time that it took to install the load center and the circuit breakers inside of the load center. And the final goal for this project was to ensure that the easy-on load center was easier in general to install than that of its predecessors, the traditional load center and the plug-on neutral load center.
Current progress with DB&T goals. A Siemens plug-on neutral load center and breakers were donated, so the easy-on system has been built off of that. 3mm aluminum legs were cut on the bandsaw to fit into the back of the breaker. These legs allowed for the breaker to plug into the slide connectors. The slide connectors were welded to screw connectors to accept the hot and neutral wires from the circuit. Testing for continuity to verify the easy-on breaker completes the circuit, and average times were taken to install and replace each breaker type.
In this flowchart, it is shown that the line voltage of 120 volts, 240 volts leads directly into the main 100 amp breaker and then is split into two hot bar, pole A and pole B. On pole A, it is shown that the easy-on GFCI breaker is connected via a traditional hot plug-on connector, and then the home run wire, traditional neutral wire, and plug-on neutral bar are all connected with easy-on plug-on connectors. Conversely, the hot bar for pole B is connected with a traditional hot plug-on bar to the traditional GFCI breaker. Then screw-on connections are made to the home run wire, the traditional neutral wired connection, and pigtail neutral connection.
Final steps of this process. The final design has been refined with professional help from Bill Womack, and the testing fields were decided and tested. Timing of installation for the easy-on breaker versus the current products was tested and analyzed with longitudinal testing. In these tests, the breakers were installed, wired, and the times were recorded for such installation. Also, a cost analysis for the easy-on load center was created along with a timing diagram. For this cost, the average hourly rate for entry-level and master electricians was used, and the timing diagram was simply just how long it took to install each breaker type in each load center type.
So for the research section of this project, we utilized longitudinal repeated measures to measure the total and average amount of times that it would take to install each circuit breaker type into each load center type. And we also utilized labor cost analysis to determine the total amount of money that it would cost to install the circuit breakers into the load centers. Now, in the end, what we did was we compared the longitudinal repeated measures to the cost analysis to determine the total amount of time and money it would cost to install circuit breakers into each different load center type. And our ultimate goal here was to determine whether or not our easy on load center was actually more efficient in terms of the time of installation as well as cost than that of its predecessors, the traditional load center and the plug-on neutral load center.
Longitudinal time testing per breaker type. Each breaker was installed multiple times, and times were collected to gain an average time. The easy-on average time was 39.4 seconds, the plug-on neutral average time was 47.7 seconds, and the traditional breaker average time was 60.9 seconds. As you can see, the Easy On is faster, but not much due to the fact that with the install, the same amount of wires need to be landed.
By reviewing this cost analysis for installation of panels chart, it can be seen that the Easy On breaker system is significantly less as compared to the plug-on neutral and traditional panel. The Easy On system resulted in a reduction of install time of about 35% as compared to the traditional breaker system, and about 17% reduction in time as compared to the plug-on neutral Siemens system. We can see that the cost for the Easy On panel can be as low as $34 with an average of $39 for a $100 an hour master electrician to install a 36 breaker panel, versus a traditional breaker panel could cost up to $103 for a 36 breaker panel with an average of $60 per panel.
In this slide, the cost analysis for installation of each panel is shown. You can see the hourly rate for entry-level and master electricians installing 36 breakers. You can see in the charts that the Easy On load center is cheaper and takes less time for installation. This is important because it proves that this new system is going to be more cost effective and save a lot of time for electricians and contractors on the job.
Maintenance time for breaker replacement. Here the Easy On was compared to the plug-on neutral. The average time to replace an Easy On breaker was 5.063 seconds. The average time to replace a plug-on neutral was 33.67 seconds. This is where the Easy On breaker truly shines, due to the fact that no wires need to be disconnected or reconnected when replacing a breaker.
Challenges. Change of design from a completely pre-wired load center to an easy plug-on breaker system. There were difficulties deciding how to properly test how long installation of the Easy On breaker system would take as compared to a traditional load center and a plug-on neutral load center. Initially, there were difficulties finding an electrician to assess the feasibility of our Easy On system. Only Siemens, General Electric, GE, and ABB breakers and panels were used in the design and testing process. Additional challenges. Several testing limitations were brought on by the KSU Safety Department regarding live testing of the Easy On load center. Also, labor price estimates are based on 2022 labor costs with unknown future price predictions. The statistical methods that are used to identify the time of circuit installation are limited to the installation of one circuit per load center. After review, Bill Womack pointed out that the Easy On breaker failed to supply a connection for a return neutral on GFCI type breakers. Installation times were not substantially faster with the Easy On system.
In this slide, the successes of this research is shown. The build of an Easy On load center was successfully accomplished. Using combined ideas, the design was implemented using products that were already available through Siemens plug-on neutral load center. This plug-on neutral load center was modified to fit the new design with the Easy On system. The connection to the circuit's hot wire and the return neutral was created using Easy On connectors. This design will work for all breaker types. Maintenance times were 85% faster with the Easy On system when compared to a plug-on neutral system, meaning whenever a contractor has to change a breaker due to failure or some other circumstance, the reinstallation of an Easy On breaker was 85% faster than on a traditional plug-on neutral system. Concluding remarks for this design, build, and test process. Currently, an electrical panel is a box that holds many different circuit breakers. Wires from the house, aka home runs, are installed into the circuit breakers, and then the circuit breakers are then installed into the load center. The electrical panel is attached to a power source, aka the main grid, from outside, and then that power is supplied to the circuit breakers that then supply the power to different parts of the house, like the bedroom and the kitchen. The EasyOn system was designed to allow a quick installation of the circuit breakers, streamlining the process for contractors installing the load center. While the install times were faster using the EasyOn system, it was by a very small margin. However, when it comes to replacing an EasyOn breaker, there is no wiring to be done, and the time saved is greatly increased. This also limits the opportunity for mistakes or injury during the installation or maintenance process.
Hello everyone, my name is Kellen Bellis. This is the final presentation for the Summer 2022 Senior Project at Kennesaw State University. The topic of this presentation is over the design, build, and testing of a capacitive energy harvester. This presentation is done by Group B, which consists of teammates Fareed, Behrooz, Caleb, and myself, working under the guidance of Dr. Okayo. Energy harvesting is known as the process of capturing forms of ambient energy with the goal of powering devices with it. AC power lines form an electromagnetic field around the line in proportion to the current and voltage of the line. The capacitive method of energy harvesting can be utilized by placing a conductor near the power line's electric field, and by doing so, a charge is collected on the conductor, resulting in a harvested voltage potential from the stray electric field. For the proposed project design, the conductor used will be a copper tube and an aluminum tube. After a voltage potential is generated on the conductor, this can be used as an input source to a rectifier circuit, which will produce a smooth DC voltage. This DC voltage will be stored into a supercapacitor, which will send bursts of power to the microcontroller, which will allow for data to be collected in short bursts, preferably every couple of minutes. Experiments will be constrained due to being in a controlled lab environment with a source voltage of 120 volts RMS. Initially, the team's plan was to decide on a best design for a harvester and circuit by using LT-Spice simulation. Since the harvested voltage was very little, this voltage would need to be stepped up using a transformer. Then, this would need to be converted from AC to DC using a rectifier and regulated using a voltage regulator in order to supply the appropriate amount of power to devices. The LTC3109 was originally chosen as it is an energy harvester chip made for low input power applications, and it has a transformer, rectifier, and regulator all in one. However, there were complications in getting the LTC3109 to operate properly since the harvested power was too low. After realizing that the harvested power was too low for the LTC3109, a different way to boost the harvester power was found, as well as a different application. By increasing the length of the tube and decreasing the diameter of the tube, the team rid the need of a voltage booster. After achieving a higher harvested voltage, the next steps can be implemented, which is rectifying the input signal and storing this DC voltage into a capacitor to supply short bursts of power to a calculator. The flow of power is shown in the following flowchart. The power line is first inserted into the copper tube, generating a voltage on the copper. This harvested voltage is then used as an input to a rectifier circuit, converting from AC to DC, and then the DC voltage is stored into a capacitor, which will be used to supply power to a small calculator.
The voltage was harvested on a 2 feet length by 1 inch copper tube with different insulators. The insulator used in the first figure was styrofoam. The voltage before the insulation was 0.168 volts and the voltage after the insulation was 0.928 volts. The output current in both the cases was 0 amps. The second figure uses a rubber hose as the insulation. The voltage before the insulation was 0.152 millivolts and the voltage after the insulation was 0.743 volts. The current in both the cases was 55 microamps. The third figure doesn't use any insulation and only uses the copper tube. The voltage before the insulation was 0.133 volts and the voltage after the insulation was 0.818 volts. The current in both the cases was 30 microamps. The length of conductor and wire is directly proportional to the electric field and harvested voltage. As length of conductor and hot wire increases, the harvested voltage also increases. The diameter of the conductor also plays a huge role on the harvested voltage due to the Coulomb's law K Q1 Q2 over R square. The voltage harvested is inversely proportional to the square of radius of conductor. Hence, as radius decreases, voltage harvested increases. Different lengths of copper tube used in this project are 2 feet, 5 feet and 10 feet, and aluminum foil length was increased every 2 feet. The different diameters of copper tube used in the project are 1/4 inch, 1/2 inch and 1 inch. The relationship between the voltage harvested and length of wire is shown in the table and plot here. As length of wire is increased every 2 feet, the harvested voltage also increases proportionally in a linear manner. It is evident from the trend line and the straight line equation from the plot. The relationship between the voltage harvested and the diameter of the copper tube is shown in the table and plot here. As the diameter of the copper tube is increased from 1/8 inch to 1/4 inch and then 1/2 inch and 1 inch, the voltage harvested decreases in exponential manner due to the Coulomb's law. The harvested voltage is inversely proportional to the square of the radius of the copper tube as seen from the plot here. The source voltage used for all experiments in the project was 120 volts VRMS. The table here shows the estimated values of harvested voltage and current for different values of transmission line voltages. As seen from the table here, as transmission line source voltage increases from 120 volts to 240 volts and then 4000 volts, the harvested voltage and current also increases proportionally in linear manner.
Copper and aluminum conductors were both tested for this project. Originally, only copper was going to be used since it's the better conductor, but unfortunately, copper tubes only come in fixed diameters. And according to Coulomb's law, the further away the conductor is from the electrical wire, the smaller the electrical force there will be on the conductor. To make the distance between the wire and the conductor as small as possible, aluminum foil was used for the conductor and was tightly wrapped around the wire to get as small of a radius as possible. Now that a voltage was being induced on the conductor, experiments were done to see if the harvested energy could be turned into usable power by rectifying the alternating current from the conductor to direct current that could power small devices. The conductor used here was a 1/2 inch, 10-foot long copper pipe. A diode was connected to the output of the conductor, which can be seen in Figure 9. In Figure 10, an oscilloscope was used to measure both the input voltage, shown in yellow, and the output voltage, shown in green, and it was found that the output voltage was a half wave with about 3.3 volts. To smooth out the half wave that was produced by the addition of the diode, a small capacitor was added to the circuit in parallel to the load. Here's the LT-SPICE schematic that was created to determine the exact capacitance of the capacitor. The battery represents our conductor with a frequency of 60 Hz and an amplitude of 19 volts. This slide shows the input and output voltages when the previous circuit was simulated in LT-SPICE. The green output is a smooth DC signal now that the capacitor was added. The previous test was conducted again with the addition of the 56 nanofarad capacitor added to the circuit, which can be seen in Figure 13. The oscilloscope in Figure 14 shows the output is much smoother than the half wave that was previously produced, but unfortunately output voltage reduced to 2.83 volts. To increase the output voltage, the input voltage needed to be increased, and to achieve that, the diameter of the conductor needed to be smaller. To decrease the diameter of the conductor, aluminum foil was used instead of the copper pipe because it was able to be tightly wrapped around the wire. The output was connected to the same circuit as before, and both the input and output voltages were measured. As shown in Figure 13, the input voltage increased to 39.7 volts peak to peak, and the output increased to 10.2 volts, while still maintaining its sawtooth shape. Failures. Rectifying the output voltage from the copper rod from AC to DC. The output voltage steps down from 10 volts AC to 1.6 volts DC. The full wave bridge rectifier created using diodes and capacitor gives desired output DC voltage when used with a signal generator, but doesn't give desired output when used with copper tube. The AC to DC converter bought from Amazon also doesn't give the desired DC output voltage. The output DC voltage has ripples, and it needs to be filtered using appropriate capacitor and resistor.
Successes. Since it is known by the Coulomb's law that the electric field is proportional to the length of the conductor, and it is inversely proportional to the square of the radius of the conductor, so the longer conductor copper was chosen with a small radius. So the voltage was in the desired range, and the voltage booster circuit wasn't required. So based on different applications and the desired voltage, so the length and radius of the conductor can be modified to get the desired voltage. Final steps. The microcontroller needs to be programmed to quickly turn on and take the data. So basically, this is how microcontrollers are working. They wake up every 10-15 seconds. They collect data like temperature and humidity, and then go back to sleep and then repeat the same thing. So they need a way to generate more current from the harvester circuit in order to power the microcontroller. So for this reason, the full bridge rectifier is implemented. Limitations and future work. When the aluminum foil was used to get as close as possible to the cable to maximize the DC voltage, the voltage was in desired range, but the output current was very small, in the range of 16 microamp. So as a result, the power would be in a microwatt as well. So with this kind of power, it is not possible to power up the microcontroller. The future task would be to find a way to increase the output current. One of the potential solution can be using the copper foil instead of aluminum foil, because copper foil has a better conductivity. Concluding remarks. So far it is determined that the copper conductor can be used to collect the charge from the transmission lines. It is also determined that the electric field is proportional to the length of the conductor, and it is inversely proportional to the square of the radius of the conductor. It is also determined that the frequency of the signal from the transmission line matches the signal frequency of the copper conductor. So the only challenge is to find a way to convert the AC signal to the DC signal in a usable range to power up the microcontroller.
The following video demonstrates the relationship between the length of the conductor and the amount of voltage harvested using the 10-foot copper tube. From the video, one should be able to see the harvested voltage increase as length increases. Furthermore, another demonstration involving the aluminum foil harvester and rectifier circuit is shown. The input signal and output signal measurements are taken on the oscilloscope to show a visual of the signals.
This is a demonstration of our copper harvester. We'll show as you increase the length of the 120 volt line going in, the voltage will increase as well. So as we're feeding it in, we're already up to 1.3 volts. All right, we're up to 2.5 volts. 9, and we're out the other end. So the max we'll get for this 10-foot harvester is about 9. 8.6 is what it's reading right now. This is a demonstration of our half-wave rectified circuit. We start with approximately a 2-foot wire that's wrapped in aluminum foil. The aluminum foil is the harvester. The line is 120 volts. It's connected to our circuit here. This is the input to a diode, which goes to a 56 nanofarad capacitor. And then it comes out to the oscilloscope. The input signal shows 2.648 volts, and the output is a sawtooth DC, which shows 1.09 volts.